So, why do AI voices in low resource languages still sound so unnatural? It's a question that honestly plagues the whole field of speech synthesis. Look, if you've ever tried building a text to speech system for a language that just doesn't have massive, highly annotated datasets, you know the exact struggle I'm talking about. You feed the system text, but what actually comes out is robotic, it's flat, and it's totally stripped of all those unique little nuances of a real human voice. It's a major frustration. The voice completely lacks emotion, misses local accents, and just fails to capture the true essence of the speaker. Well, today, we're going to unpack a massive breakthrough that might just solve this persistent issue for good.
Welcome to This Explainer. Okay, today we are looking at a truly revolutionary new approach in text-to-speech, or TTS, called SPARCLE. And guys, this isn't just some incremental little update. It is a fundamental shift in how we actually map written text to spoken audio. For literally decades, researchers have had to rely on these clunky intermediate steps to get from a written letter to an actual sound. SPARCLE changes that whole paradigm by completely eliminating one of the oldest, most stubborn bottlenecks in the entire TTS pipeline. So get ready, because this methodology is absolutely going to change how we think about low-resource speech synthesis from here on out.
Okay, let's dive right into this. Here is our roadmap for today. 1. The problem with G2P. 2. Enter SPARCLE. 3. Contrastive alignment mechanics. 4. Breaking down the data. And 5. Integrating SPARCLE into your pipelines. Starting right off with Section 1, the problem with G2P, the traditional TTS bottleneck. Right, so in traditional pipelines, the primary culprit for our headaches is grapheme to phoneme, or G2P. Its whole job is to bridge written text, the graphemes, and the sounds they actually make, the phonemes. And to be fair, it's been necessary because characters often have one-to-many mappings. Think of the letter C in the word cat versus cell. But here's the fatal flaw with this setup. GTP relies heavily on these massive external pronunciation dictionaries. And creating those, it takes hundreds of hours of expert linguistic work, which just does not scale. Worse than that, during this conversion stage, the system completely strips away speaker-specific acoustic variations. It basically treats all voices as if they're phonetically identical. By forcing text into standardized phonemes, you're essentially throwing away incredibly valuable acoustic details, like a speaker's unique cadence or maybe a breathiness in their voice, right at the very start of your pipeline.
Think of the traditional GDP pipeline as basically a really high-stakes game of telephone. Because it operates in these cascaded, step-by-step stages, if a phoneme is mispronounced, vaguely defined, or just incorrectly mapped at the very beginning, boom, that error is locked in permanently. It travels all the way down the line, corrupting literally every single downstream acoustic prediction. By the time that data reaches your vocoder at the completely other end of the line, it's way too late. The vocoder's only job is just to generate the waveform from whatever data it receives. It has absolutely zero chance of fixing an error that was baked in at the symbolic level moments earlier. You end up with audio that sounds glitchy, unnatural, or just straight up mispronounced. So this current paradigm utterly fails when data is scarce. If you're working in a low-resource environment, you just don't have the luxury of building these exhaustive external pronunciation dictionaries. You're forced into a really hard dependency on lookup tables that might not even exist for your target language or a specific dialect. And because the traditional method strips away all that speaker-specific prosody, any voice you do manage to generate just sounds entirely generic and lifeless. You lose the regional dialects, you lose the emotional undertones, and you lose the individual character of the speaker. We really needed a way out of this rigid, dictionary-dependent trap.
Which brings us to Section 2. Enter SPARCLE, a whole new approach. Meet SPARCLE. Yes, it stands for Speaker-Aware Aligned Representations via Contrastive Language Embeddings. I know, it's a total mouthful, but the core concept here is just beautifully elegant. SPARCLE completely removes that G2P bottleneck. Instead of forcing text into those rigid intermediate phoneme simples, this model enriches the raw characters directly with precise acoustic realizations. It is a total paradigm shift for sure. You feed it graphemes and it maps them directly to the acoustic space, conditioning them on the actual speaker. This means the model learns exactly how a specific person pronounces a specific letter in a specific context, rather than relying on some generalized dictionary rule. When we compare the two architectures side by side, it's literally night and day. The traditional GDP system over there on the left suffers from those cascading errors. It's highly error-prone, and it inevitably results in that generic voice averaging we talked about. Every speaker just sounds like a robotic average of all the training data.
But Sparkle on the right gives us this single unified text-to-acoustic mapping layer. It is inherently speaker-aware, which means it preserves the unique articulation, pitch, and prosody of the individual voice. And it's incredibly robust precisely because it doesn't need those massive external dictionaries. It learns the pronunciation directly from the raw audio, making it infinitely more scalable to new, undocumented languages.
Section 3. Contrastive alignment mechanics. Let's look under the hood.
So, what's actually powering this? Well, the foundation of Sparkle is its acoustic backbone, and the researchers went with a really powerful one, Wave-to-Vec2. This is the engine that bridges the two entirely different worlds of discrete text characters, the graphemes, and continuous acoustic sounds. Wave-to-Vec2 is fantastic at extracting these incredibly rich frame-level features from raw speech data. By leveraging this established self-supervised model, it gives Sparkle the highly detailed acoustic map it needs to start connecting the dots between what is written and what is actually spoken in the audio recording.
Okay, so how exactly does it connect those dots? It uses contrastive learning. During training, the model applies a contrastive objective that acts kind of like a giant magnet. It strongly pulls the grapheme tokens toward their correct matching acoustic frames, and simultaneously pushes unrelated sequences far apart. But here is the real secret sauce. It uses speaker identity as a conditioning variable. By constantly reminding the model who is speaking, the contrastive loss function acts as this powerful regularizer. It completely prevents the grapheme representations from collapsing into a generic average voice. Instead, it literally forces the network to retain fine-grained, voice-specific acoustic distinctions for every single character.
To summarize just how elegant this architecture is, I want to read this quote directly from the research paper. Sparkle is, quote, learning a joint embedding space where character tokens map to their exact acoustic realizations without intermediate symbolic conversion. We are completely skipping the middleman here. No intermediate phonemes to manage, absolutely no linguistic dictionaries to keep updating, and no phonetic transcribers required. Just a direct, highly accurate mapping from raw text straight into continuous sound. Let's move on to Section 4, breaking down the data, or the performance proof.
50%. I just want that number to sink in for a second. When the researchers tested Sparkle in extreme low-resource conditions, which is the exact environment where traditional models just fall apart, Sparkle achieved a massive 50% drop in the word error rate, or WER. It literally cut the errors entirely in half compared to standard grapheme-based approaches. Now, in the world of speech synthesis, where a drop of even 5 or 10% is celebrated as a pretty major victory, cutting the error rate in half, that is a monumental leap forward for language accessibility.
And this chart brilliantly illustrates exactly what we're talking about. While high-resource settings might favor standard graphene models just due to the sheer volume of data, the second your training data drops, traditional models spike in errors. They just can't generalize without enough phonetic examples. Sparkle completely reverses that trend. It matches or even beats phoneme-based performance, and it achieves this impressive feat without requiring a single G2P lookup table. This proves conclusively that speaker-conditioned alignment preserves intelligibility and naturalness even when you barely have any acoustic training samples to work with in the first place.
Now, for the researchers out there wanting to really dig into the rigorous ablation studies, the team's 5-page interspeech paper is available open access right now on arXiv under ID 2607.01238. Published by Mazumdar and the team, it's just a fantastic blueprint if you want to understand the exact contrastive loss formulations or see how the model behaves across different language families. And because it's under a Creative Commons license, it is fully accessible to anyone looking to replicate these state-of-the-art results.
Section 5, Integrating Sparkle into Pipelines. Here's your developer action plan.
Obviously, replacing a G2P module means adjusting how your text enters the acoustic generation stage. The good news is Sparkle is designed to slot really cleanly into existing encoder-decoder frameworks, but you do need to follow these 4 actionable steps. First off, pre-process your text strictly into character-level tokens. Just leave the phonemes behind entirely. Number 2, and this is crucial, inject your speaker embeddings or IDs into the model input to condition that alignment. This is the absolute linchpin for retaining that unique voice identity. Third, feed those newly aligned Grapheme acoustic representations directly into your vocoder. And finally, step 4, retrain or fine-tune your downstream TTS head using these new joint embeddings. Follow these steps, and you completely eliminate the severe overhead of maintaining those old G2P systems.
Oh, and I definitely want to leave developers with this fantastic pro tip straight from the paper. When you're adopting this alignment to a new domain, let's say you're moving from audiobooks to conversational podcasts, take the time to retrain the contrastive objective on your domain-specific speech data before you fine-tune the acoustic decoder.
Actually, this two-stage approach is the absolute key to preventing representation drift. It ensures the model doesn't just forget how to map characters to sounds accurately, making sure you maintain all those beautiful speaker conditioning benefits across totally different audio styles.
Ultimately, Sparkle is showing us that the old, rigid, dictionary-dependent ways of building TTS systems are fading, and they're fading fast. By leveraging contrastive learning, developers can now map text directly to rich, speaker-specific sound, ensuring high quality even in the absolute most low-resource languages around the globe. It's just a massive leap forward for accessibility and natural-sounding AI, proving we no longer have to sacrifice voice identity for intelligibility. So as the G2P bottleneck fades into history, what other long-standing linguistic bottlenecks will contrastive AI eliminate next? The possibilities are pretty endless. Thanks for joining me on this explainer, and keep building.